Hey guys, welcome to another session on maths for data sciences. So here we'll be starting with the probability distribution functions. So for that, we need to understand what a random variable is. So this was actually covered in one of the previous sessions. So a random variable we denote by a capital X, let's say, and the random variable is nothing but an outcome of a random experiment. So now let us say we have a dice and it's a fair dice. So all the 6 values of dice are equally likely, and the each probability could be given as 1 by 6 since there are 6 faces in the dice here. So in this case, X represents output of dice, and the values of X could be 1, 2, 3, 4, 5 or 6. So if you remember, this is also called the sample space of the random experiment. So now that we know X is a random variable and we have got a certain distribution of the probabilities for each value of X, this is nothing but this is called the probability distribution function of X. Now this is also called the PMF of X, where PMF is nothing but probability mass function of X. Now one thing to note here is whatever right now we are doing is only valid for discrete distributions. Now what is a discrete distribution? X can only take countable values here. Now we know that X in this case can only take 6 values, and therefore X is a discrete random variable. So X is a discrete random variable because it can take a limited countable number of values. It cannot take infinite number of values in a particular range of X. Now that we know what is a discrete distribution function, or we can call this a probability mass function of X, let us say we want to plot this kind of a function in a particular graph. So how do we do that? We use something called a histogram to plot the PMF of X. So PMF is nothing but probability mass function of X, and we call the X-axis as the values of X basically would be given in on this axis. So this is 1, 2, 3, 4, 5 and 6. Now since this is a discrete random variable, we have, and also all the probabilities are equal here. Let's call this point as 1 by 6. We simply put the points here. For all the 6 values, we know that they will be at 1 by 6. Therefore, if we look at the densities here, so these should actually be joined, otherwise it becomes a bar chart. So it would look something like this. So histograms normally are made for a particular range of values. So in a way, we can call these to be made as P 0.5 to 1.5 equal to P 1.5 to 2.5, so on till P 5.5 till 6.5 to be equal to 1 by 6. So just to convert the discrete random variable in a particular binning form, By bins I mean 0.5 to 1.5. So why we did that because there's only one value x equal to 1 which lies in the range 0.5 to 1.5, and similarly 1.5 to 2.5 there is only one value of x equal to 2, and all these values of x have a probability equal to 1 by 6, and therefore we obtain a particular histogram in this case for this particular distribution function. Now that we know what is a probability distribution function or probability mass function for a discrete random variable, which means it can only take limited number of values of x, we will look at some of the standard distribution functions which will be used a lot in statistics. So we'll be seeing only a few ones which are very important from data science perspective. So these are uniform distribution, then we have something called binomial distribution, then we have Bernoulli's distribution, then we have geometric distribution, and something called a Poisson distribution. So we'll be covering the first three in this particular session, and we'll be leaving the rest two for the next one. So first, moving to uniform distribution function. This is all the probabilities are equal here for the given values of x. So in this case, Px equal to x is equal to k for x equal to some values, let us say n values, and Px equal to x equal to 0 for other x. So the value of probability is non-zero and equal to k only for these n values of x, and otherwise it is always 0. So now we will look at a very important property here. Sum of all probabilities is always 1. So if you guys remember from our very first few sessions, we saw that the sum of probability across all the outcomes should always be equal to 1. Therefore, if for each of the n values here we have the same probability k, the sum of n times k should be equal to 1. So basically we are just summing up k n times to get total probability as 1, and therefore k should be equal to 1 by n. Now a very basic example of this is nothing but the dice roll, which we saw in this session itself, in fact. So in that we had n equal to 6 faces which were all equally likely. Therefore we had got k equal to 1 by 6, and thus the PMF was defined as Px equal to x as 1 by 6 for x equal to 1, 2 till 6, and Px x equal to 0 otherwise. So this is how we define a PMF or a probability mass function for a discrete uniform distribution. So next we move to binomial distribution. So this will be looking at through an example. Let's say we are trying to predict rain on each of the next n days. So we also know the probability of rain on any day is P, and also all the days are independent of each other. So this is a very important assumption here. All the days, the probability of getting a rain remains P irrespective of what happens in any of the other n days. So that is what it means by independent here. So if you remember in our sessions on probability, independent events are the ones where the probability of a certain event happening does not change given that that particular event happened on any other trial. So that is the exact independence definition which we are using here. Now, if we know that there is a rain happening with a probability of P on any of these n days, let us say now we have to calculate the probability of rain happening. So X in this case, X random variable here defines the number of days out of n when event occurs, which means in this case rain happens. So this is a binomial random variable where the random variable is defined as the number of days or number of trials out of the total n trials in which the event occurs. Now if we want the value of this random variable to be x, how we are going to calculate it? So you need to refresh your permutations and combinations from the previous session here. How we calculate this is we look at the total number of ways to select x out of n days. So this we are selecting because we want x out of the n days to have rain, but this x number of days could be any x number of days. So it could be day 1, 2 and 3. Let us say we have x equal to 3. Now x equal to 3 could have we could have rain on, let's say, days 2, 3 and 5. We could also have it on 3, 5 or 6. Let us say n equal to 10, which is that we are looking at total of 10 days. And then we can also have it in 4, 7, 6 or 8. So there are many such combinations, and the total number of combinations is computed as total number of ways to select 3 out of these 10 days. Then we also need probability of rain in those x days selected, and the probability of no rain in the remaining n minus x days. We have rain in x out of the total n days, and therefore we will not have any rain in the remaining n minus x days. Now we know that the total number of ways to select x out of the n days is nothing but the combination operator NCX. So we are selecting x out of the n days where the rain will happen. Now the probability of rain in those x days is to be calculated, which is p into p x times. So this becomes p raised to power x, and the probability of no rain in the remaining n minus x days would be 1 minus p raised to power n minus x, because the probability of rain on any day is p, therefore the probability of no rain in any of those days would be 1 minus p, and there is no rain in n minus x total days. So we raise the power of 1 minus p to n minus x, and for rain days we have p raised to power x here. So this is called the probability mass function for a binomial distribution. Now let us say we look at an example. Let us say we look at our same example which we saw earlier. So px equal to 3, and we have n equal to 10, and let us say the probability is 0.5. Now we calculate this as 10C3, 0.5 raised to power 3, 1 minus 0.5 raised to power 10 minus 3. So this is 10C3 point. So in this case, this is also 0.5. So 0.5 raised to power 7 into 0.5 raised to power 3 is 0.5 raised to power 10. And we can now calculate this easily since we know how to calculate the combination operator. It is calculated as 10 factorial upon 3 factorial as 10 minus 3 factorial. This is 10 9 into 8 divided by 6. So this becomes 4 3. This is 120. So we get the value as 120 into 0.5 raised to power 10. So this is how we define a binomial distribution function, as well as this is how we calculate the binomial probabilities for any binomial random variable for different values of x for a given values of n and p. So one more thing I wanted to show here is whenever we are given a particular distribution, let us say a binomial distribution, we write it as so x is the random variable, binomial random variable. We write it with a single tilde and we denote it by bin, binomial, n equal to 10 in this case and p is equal to 0.5. Now this particular binomial distribution has two parameters, n and p, for which the distribution is defined. So these are called the parameters of the distribution. So binomial distribution clearly has two parameters for which are required to calculate the probability for any value of x. We calculate it for x equal to 3 in this particular case. Now moving on, we wanted to look at the third kind of distribution, that is Bernoulli distribution. Now Bernoulli distribution is a special case of binomial distribution where n is equal to 1 and the probability is denoted by the parameter theta, and here the notation of the distribution could be written as Bernoulli theta. Now since n is fixed here, we only have one parameter here, which is theta. So there is one parameter which is theta, which is same as the probability we saw in the binomial distribution, but in this case we only have, since n is equal to 1, we have only one trial. Now one can automatically guess the possible values of x could only be 0 or 1. Note that in case of binomial distribution, which we saw here, the possible values of x could have been 0, 1, 2 and so on till n, which is 10 in this case. Why? Because x is nothing but the total number of events that happen out of total n trials. So it is possible that the event or the rain occurs in each of the 10 days, and therefore the maximum value of x could be 10, and it is possible that the rain never occurs in any of those 10 days, and therefore the minimum value would be equal to x equal to 0. And in this case, Bernoulli, since there is only one trial, the possible values of x are 0 or 1, and the probability mass function here would be given as p x equal to 0 as 1 minus p since the event doesn't occur, and p x equal to 1 as p. And as you can see, the sum of the probability is 1, and p is nothing but the probability of that event to occur on that single trial. So we looked at uniform distribution, binomial distribution and Bernoulli distribution, which was a special case of binomial distribution with only one trial in this particular session, and we'll be looking at the rest two distributions along with some Python implementations in our next session.